welcome to this deep dive. Today we're taking on a challenge, really. It's something straight out of a theoretical physics conference.
It really is. We've basically been handed a set of, 15 technical slides, a presentation called Unfolding Spacetime.
And we have about 15 minutes to get through it, so this is going to be a sprint. Our mission for you is to get to the absolute core of the geometry and the dynamics here.
Exactly. We're aiming to connect the dots between some pretty high-level math. We're talking symmetry groups, dimensional reduction, and what it all means for the final description of a black hole.
So this is all about the Lemos hypercylinder. We're going to be focusing on how finding the right symmetries is, well, it's the ultimate shortcut to solving these incredibly complex equations.
It's the only way, really. So slide 1, let's just jump in. The theme is symmetry and dimensional reduction.
Okay, slide 2. Let's set the stage. What exactly is this object we're studying?
So we're looking at a black hole solution, but one with cylindrical symmetry. It exists in a 4-dimensional spacetime. That's 3 plus 1D.
And there's a crucial constraint here.
A very crucial one. It has to have a negative cosmological constant. Lambda is less than 0. That's a foundational requirement for this kind of geometry to even exist.
And the challenge, right, is that if you just try to analyze its full 4D dynamics, looking at all the metric tensors and whatnot.
Oh, it's computationally overwhelming. The solutions are they're practically impenetrable. You can't interpret them.
Which is why we have to find another way in. We have to simplify.
Exactly. The complexity forces you to look for a hidden blueprint, some underlying structure.
And that blueprint, which is slide 3, is this fundamental symmetry group, O22.
Yes, O22. This is the group of all the transformations, so your rotations, your boosts, that leave the space-time interval, the distance on this manifold, completely unchanged.
Okay, so let's just quickly do the dimension math here. For a group OPQ, the dimension is what? P plus Q times P plus Q1 all over 2.
That's the one. So for O22, you plug in the numbers and you get 6, a 6-dimensional group of isometries.
6 dimensions. That's a lot of symmetry. That's the key, right? It tells us the problem has a huge amount of redundancy we can, well, exploit.
Precisely. And that brings us to the next slide, the real conceptual breakthrough, the connection to lower dimensions.
This is the isomorphism.
The critical isomorphism, yeah.
Right.
It turns out that O22 is mathematically equivalent to the direct product of the special linear group SL2R with itself.
So O22 is isomorphic to SL2R times SL2R.
Yeah.
Now, for those of us not using group theory every day, what exactly is SL2R?
Right, so SL2R is just the group of all 2x2 real matrices that have a determinant of exactly 1.
And why is that specific group so important?
Because, and this is the beautiful part, SL2 is also the isometry group of 3-dimensional anti-de Sitter space, ADS3.
Ah, okay, so that's the bridge.
That's the entire bridge. That one piece of math is the Rosetta Stone. It connects our complicated 4D spacetime to a much, much simpler 3D description that we can actually solve.
So the very structure of our 4D hypercylinder is built from the symmetries of 3D anti-de Sitter space. That's a huge shortcut.
A massive one. And we can visualize this, which is our next slide. The geometry of SL2R can be mapped onto these 3D surfaces. And the shape of those surfaces, hyperboloids, cones, and so on, it's all dictated by the eigenvalues of the transformation matrices.
Which tell you if the motion is elliptical, hyperbolic, that sort of thing.
Exactly. And that geometric insight lets us do the final construction step. We use a quotient space.
We're basically going to build our cylinder from a hyperbolic plane.
That's right. We start with a slice of ADS3, which is the hyperbolic half plane H2. It's infinite.
So you need to make it finite. You need to glue it together.
We introduce a gluing instruction. We take a discrete transformation from SL to R, we call it A, and we apply it. The map is Z goes to E to the 2 lambda times Z.
In that action, it takes this infinite plane and rolls it up.
In essence, yes. It transforms the infinite half-plane into a surface that is topologically a cylinder. And that cylinder becomes the spatial boundary of the black hole we're trying to describe, the BPZ black hole.
Okay, so we've established the deep math. Let's move to the physics of the 4D hypercylinder. How do these symmetries actually show up?
We look for the killing vectors, the generators of the symmetry. And in the simplest case, there are 3 key translational symmetries.
Right, these are the more intuitive ones. First, you have stationarity. The metric doesn't change with time.
That's your partial T.
Then axis symmetry. It's independent of the rotation angle.
Partial phi.
And the third, the linchpin for this whole thing, longitudinal invariance. Partial Z.
And that's the key. It means the geometry is the same no matter where you are along the central axis of the cylinder. That independence from Z is what makes dimensional reduction even possible.
But, and this is a huge, but we had a complication, a real black hole has mass.
And as soon as you introduce linear mass density, B greater than 0, you break the symmetry. 4 of those 6 beautiful O2 over 2 symmetries just vanish.
So only stationarity and axis symmetry are left. That seems like a deal breaker if the Z invariance is gone.
You'd think so. But here's the insight. While that symmetry is broken near the black hole, it gets restored asymptotically as you go very, very far away, as R goes to infinity.
It's not the same symmetry, though, is it? It changes form.
It does. The translational symmetry, partial Z, effectively gets remapped into a scaling symmetry. It becomes R partial R minus T partial T.
So it's not that we can ignore the Z coordinate anymore, but because the structure is invariant under scaling at the boundary, we can still systematically remove it.
Exactly, and that allows us to perform the central maneuver here, trading a dimension for a field. This is Kaluza-Klein dimensional reduction.
We integrate out the Z coordinate.
But we're not just deleting it. This is the crucial part. All the physical information that was contained in that Z dimension gets conserved. It's encoded into a new dynamic variable in our new lower dimensional theory,
The
dilaton field. We make a clean trade. One spatial dimension, Z, becomes mathematically equivalent to one scalar field, phi. You're converting geometric complexity into field complexity.
Okay, so let's walk through the 4 steps of this reduction. Step 1 is the metric ansatz, basically an educated guess for the metric.
Right. An ansatz based on the symmetries we know, it's structured to separate the Z dimension from everything else.
So you have the 3D part and then a term e to the 2 psi, which describes the size of that extra Z dimension.
Exactly. Then step 2, you decompose the 4D Ricci scalar. This is a bit of math that neatly separates the 3D curvature R from the behavior of our new field C psi. It decouples them.
Step 3 is the actual integration. We integrate out Z, and since nothing depends on Z anymore, it's pretty straightforward. The volume element just scales down cleanly.
And finally, step 4. We construct the new 3D action. You substitute all these decomposed parts back into the original 4D action, and what pops out is an effective 3D action.
And by defining the dilaton field, phi, as e to the minus psi, the action takes on a very specific form, the Brans-Dicke form. S is approximately the integral of phi times r.
And that is profound.
It is. The dilaton is now explicitly coupled to the curvature. The field that represents the lost dimension is now actively telling the remaining 3D spacetime how to curve.
The geometry and the field are talking to each other, so we can sum this all up in a little dictionary. The longitudinal z-axis gets traded for the dilaton scalar field.
The translational invariance we started with becomes a conformal scaling symmetry.
And the simple Einstein-Hilbert action in 4D becomes the Brans-Dicke action in 3D.
So with that whole process complete, what does the new 3D black hole geometry actually look like?
It's defined by the 3D line element. This is the equation that describes distance in this new spacetime.
And has 3 key functions in it, f, r, n naught, and n phi. Let's break those down. What do the lapse and shift functions physically mean?
Good question. So n naught, the lapse function, is basically a time constraint. It tells you how fast proper time is flowing for an observer compared to the coordinate time, t. It's a measure of gravitational time dilation.
And the shift function, n phi.
The shift function describes how space itself is dragged along by the rotation of the black hole. It's the frame dragging effect. It couples the time and angular coordinates.
Okay, so that line element sets the stage. It defines the static geometry. But we still need the rules of the play, the dynamics.
Right. And that comes from the variation of the action. This is the core principle. The equation shows how the whole system reacts to changes.
And the equation looks complicated, but its meaning is actually quite profound. It says that any change in the total action is completely determined by changes in the conserved quantities, measured way out at infinity.
Exactly. And those quantities are m, the mass line density, and j, the angular momentum line density.
Line density because the original object was an infinite cylinder.
That's right. And here's the punchline. Those two numbers, m and j, are the only two parameters you need to completely uniquely define the physical nature of this lower dimensional black hole.
So let's tie it all together, the synthesis, the complete picture of the BTZ black hole.
We can say it now. The line element defines the geometry, the stage.
And the variation of action enforces the physical laws Einstein's equations. It's the play.
And together, they give a complete description. After all that group theory, all that dimensional reduction, the entire structure boils down to just two numbers. Its mass per unit length, m, and its angular momentum per unit length, J.
It's a really remarkable theoretical journey. We started with this intractable 4D problem, the Lemos hypercylinder.
And by uncovering its deep intrinsic O2 symmetry, we found the key. We found the hidden structure of ADS3 geometry, and that gave us the mechanism for simplification.
Then we performed this highly technical trade, swapping the z dimension for the dilettante field.
And the payoff is this fully equivalent but vastly simpler 2 plus 1D BTZ black hole. It just reveals this deep correspondence between gravitational theories in different dimensions.
The elegance is really in that final simplicity. Only m and j matter.
It really is.
Now, this whole structure, this entire breakthrough, it all depends on something we mentioned right at the start. The negative cosmological constant, lambda less than 0.
Absolutely. The BTZ black hole was such a big deal because in standard general relativity, black holes just don't exist in 2 plus 1 dimensions if lambda is 0.
Why not?
You need that non-zero cosmological constant to provide a fundamental length scale. It stops the spacetime from just being locally flat everywhere. Without it, there's not enough curvature, let's say, to form a black hole.
Which brings us to a final provocative thought for you to take away. The cosmological constant isn't just some random parameter here. It's the foundation. It's what allows gravity to create these complex topological structures like black holes in fewer dimensions.
Right. Without that built-in length scale, the physics just collapses. Think about that for a second. The idea that a global property of the universe, lambda, is what enables the existence of gravity's most mysterious objects in these lower topologies.
It completely flips the script. It shows that the global structure of the universe is essential for local phenomena, especially when we step away from our familiar 3 plus 1 dimensions.
A stunning realization, all found by following the breadcrumbs of symmetry and carefully unfolding the geometry of spacetime.
Thank you for joining us on this very, very deep dive.